In this section, we're going to continue working these acid-base titration problems and just gradually building our skills with different types of problems. But don't forget that on all of these titration problems, the central theme is always the same. Basically, you have an acid and a base coming together. Usually the problem is trying to essentially ask you how much of one reactant is needed to neutralize or to titrate the other reactant. That's basically what's happening. So in this problem, we have a similar situation going on, but it is a little bit more wordy. So the trick is when you're reading these acid-base problems, you might think, a lot of students, they try to classify problems in different buckets, and whenever they figure out what bucket it's in, then they know how to solve it. Well, I'm trying to teach you not so much to do that. I'm trying to teach you how to think so that you can decipher what the problem's saying and you can figure out for yourself how to get there. So the same thing is going on here. It looks like it's a complicated problem of a different type, but once we discuss it, you'll see that it's really something that you've already been doing. You just need to think a little bit. So the problem says, what volume of sodium hydroxide, molarity of that guy is 0.550 molar. So what volume of 0.550 molar sodium hydroxide is needed to titrate a 10 milliliter sample of vinegar that is 4.12% by mass of acetic acid of CH3COOH. Vinegar has a density of 1.01 grams per milliliter. So your first thought when you read a problem like this, when we've been doing all of these acid-base reactions, you read something like this and you start thinking a lot of times, okay, this is totally different than what we've been doing. You know that it has an acid and a base in it, but because of these numbers here, like the percentage and this guy here, the density, it looks to be something totally different than what you have experience with. But you need to go back to what you know. You know that you're titrating something here. That's a huge keyword, right? And you know that there's a base involved and there's an acid involved. You should know by now that vinegar is an acid, and the acid that's in there is acetic acid. Vinegar is just a word that we use that just says that, okay, acetic acid is mixed in with water. That's all that is. That's what we call vinegar, right? So anytime you see vinegar or acetic acid, you should be thinking acid. Anytime you see a hydroxide like this, you should be thinking bases, and you're titrating it. So ultimately what you're doing is you have a certain amount of, in this case, it's an acid. It says you have a 10 milliliter sample of acid, of vinegar, right? You have a certain amount of it. And ultimately the question is, what volume of this base is needed to titrate it? So you see, when you strip everything away from the problem, ultimately it's asking you the same thing that all of the other titration problems have been asking you. It's asking you how much of this base is needed in order to neutralize this certain amount of acid that we have. In this case, the acid is acetic acid. Now there's some other numbers here, right? Not so much to confuse you, just to kind of enrich the problem and make sure you understand what we're doing. You have to kind of cut through some of this stuff to see where we're going, but ultimately that is what we're trying to do. So we have a certain amount of vinegar, which is, the acetic acid, and we'll talk about how these numbers play into it in a minute. And we're trying to figure out how much of this base is needed to fully neutralize it. So the first step of all this stuff is to write the reaction down. And it's important to do that because ultimately, no matter how we do it, we're going to need to use the reaction to calculate, to go from moles of, in this case, how much amount of acid we have to how much base is going to be required. We always need to use the chemical reaction to jump between reactants like that in basic stoichiometry. So let's write that down. We know for sure that we're going to have sodium hydroxide, and we know we're adding it ultimately to acetic acid. Now, yes, it says it's vinegar, but don't forget, vinegar just means aqueous solution. So if you really wanted to be, totally clear about it, you could say, all right, this is aqueous solution, and this is an aqueous solution. So it just means it's a water solution. Sodium hydroxide mixed in with some water, and then you have this acetic acid mixed in with some water. We call that vinegar. And they're going to do something, hopefully. Right? What do you think they're going to do? Well, it's an acid and a base, so we kind of expect it to form water. And what happens here is when this goes into water, you get sodium ions and you get these hydroxide ions. When this goes into water, this whole thing in the front, this CH3COO, this whole thing is called an acetate ion. It kind of pops off as one unit, as a negative ion. and the hydrogen is a positive ion. So this guy pops off by itself. So when you mix these guys together, much like all the other acid-base reactions we've studied so far, you get hydroxide ions floating around from the hydroxide, and you get hydrogen ions floating around from the acid. Those are going to want to form water. All right? And what's left over is going to want to combine together. So the sodium is going to pop onto the acetate here, and it's going to look like NaCH3COO. Of course, there's no H at the end. And then over here, you have H2O. And just to be totally clear, this, of course, is still an aqueous solution, and then the water is just a liquid. There's an L right over there, so that's liquid water. So literally what happens is the hydrogen pops off, the sodium goes and attaches to this acetate. This makes what we call sodium acetate, and then the HOH come together to form water. Now let's make sure it's balanced. We have one sodium, one sodium. We have 1, 2, 3 oxygens. We have 1, 2, 3 oxygens. We have 1, 2, 3, 4, 5 hydrogens. 1, 2, 3, 4, 5 hydrogens. And we have 2 carbons and 2 carbons. So everything is balanced. So the coefficients in front of everything is 1, just as we have it written here. So that's cool. All right, so ultimately we know from the problem statement that we're given a certain amount of vinegar. So this is how much we're given, right? This is how much we have sort of sitting on the bench. And it's asking us what volume of a certain concentration of this base do we need to add to titrate it. So my advice that I've always been giving you is to start with what you know. You know, look at the problem, whatever the known quantity is that you're trying to titrate, start with that. That's the total amount of what you have, and then you'll end up calculating how much you need of the other substance to neutralize it. So the only trick in this problem, and it's not really a trick, it's just the way the problem is written, is that we're told several things about the amount of vinegar we have, which is, instead of calling it vinegar, I'll try to call it acetic acid solution, because that's all it is. It's acetic acid and water. We're not given a straight answer on how much of that stuff we have. This problem would be super easy if we were told, oh, you have 5 moles of acetic acid, and you'd easily use a reaction and calculate how much base was required, and bam, you're done. But we're not given that. We're told we have a 10 milliliter sample of this vinegar, which is acetic acid solution. We're told that this solution is 4.12% by mass of acetic acid. And by the way, this number, 4.12%, that means that for every 100 milliliters, right, or for every, it's in terms of mass, so for every 100 grams of this solution in a beaker I have, only 4.12 grams of it is actually going to be acetic acid. It's kind of a way of telling you the concentration of that acid without giving you the molarity. I mean, if I just told you, hey, here's your acetic acid, the molarity of it is this, then the problem would suddenly look like a lot of other problems we've already done. You'd have the molarity and you know what to do. In this case, we're not giving you the molarity. I'm telling you, okay, here's your sample size, and oh, by the way, you're only it's only 4.12% by mass of acetic acid. It's telling you how much acetic acid is in there per unit, per percentage-wise in terms of mass. So it's telling you how concentrated this guy is in terms of acetic acid. It's also telling you that vinegar has a density of 1.01 grams per milliliter. So that should be a huge clue. I mean, it's telling you percent by mass, and then it's also telling you the density of vinegar. So let me ask you this. What can I do with these numbers? Sometimes if you don't know what to do, you need to try to look and see what you can do with these numbers and see if it inches you closer to the answer. We know we have 10 milliliter sample. That means we have a beaker or a flask full of 10 milliliters of this vinegar. This vinegar is just like what you would buy at the grocery store, right? We're also told that this vinegar has a density of 1.01 grams per milliliter. So if I know how much vinegar I have, how many milliliters, and I know that the density is 1.01 grams per milliliter, then I should be able to calculate how many grams of vinegar I have in that beaker. So let's do that real quick. So the way you do that is you say, I have 10 milliliters of vinegar. That's what my sample is. That's what's given to me and said, hey, you're trying to titrate this, right? I'm also given that this vinegar is 1.01 grams of vinegar per 1 milliliter of vinegar. Okay, so you see milliliters of vinegar cancels with milliliters of vinegar. So what you end up doing is you take 10 times 1.01. So you're going to get something real close to 10. What you're going to get is 10.1 grams of vinegar. Okay, so this is what I'm starting with. So now instead of saying, hey, you have 10 milliliters of this vinegar, I know that I have actually 10.1 grams of vinegar. It's the same thing as if I taken that beaker of vinegar, put it on a scale, and determined how much mass was contained inside that flask. 10.1 grams. And I could do that only because I was given the density. So now I know how many grams of vinegar, right? But I look back at my problem and I see, okay, they actually told me that the vinegar is 4.12% by mass acetic acid. That means that, as I said before, out of 100 grams of vinegar, only 4.12 grams of it's actually going to be acetic acid. That's what a percentage is, right? It's part over whole, right? If I have in a bucket, you know, I have some different color balls. I've got red balls and blue balls, let's say, in a bucket, right? And I'm telling you, hey, only 10% of these balls are red. Then what you know is, if you actually examine all the balls, then 10 balls out of 100 total samples, if I pull 100 balls out, then 10 of them are going to be red, if I say they're 10% red. That's what percentages basically mean. It's telling you part over whole. So when I look at this and it says 4.12%, don't gloss over it. It just means it's telling me how much acetic acid's in there. So what I can do is I can take I know how much vinegar I have. I have 10.1 grams of vinegar. 10.1 grams of vinegar. Now if I multiply that number by, you don't want to multiply by 4.12 because with percentages you always want to convert to decimal, 0.0412. So you convert this guy to a decimal. Then what you're going to get when you multiply these guys, 10.1 times this number here, you're going to get 0.4161 grams. And what are you getting? It's grams of acetic acid. That's how much acetic acid you have in your sample. So I'll go ahead and put in sample. Make sure you understand that all we're doing is we know how much vinegar we have in terms of grams, right? So we multiply by the percentage, and because we know it's 4.12% by mass, so we take 4.12% of this number, and we get a really small number. That's how many grams of acetic acid are in the sample. It should be a small number because only 4%, just over 4% of the entire sample is actually acetic acid, right? Now, if you're confused why I didn't multiply by 4.12, that is just a fact of math. When you have percentages, it's kind of like a fraction. 4.12% is really 4.12 over 100. You never multiply percentages as numbers like that because then I would be multiplying this guy by 4.12 and that wouldn't make it, we get a huge number. That wouldn't even make sense. When you use percentages in calculations, you always have to convert them to decimals. So you always end up shifting the decimal 2 places to the left. Because basically, like I said, 4.12% is 4.12 divided by 100 over 100. That's what a percentage is. So now that we know something critical, we know how many grams of acetic acid I have. Now we're getting into the realm of what we've done before, you know, because I know how many grams of acetic acid I have. So how do I get from grams to moles? Because don't forget the end game. If I can get to moles of acetic acid, then I can go to this reaction and then use the reaction stoichiometry to calculate how many moles of sodium hydroxide. And once I know how many moles of sodium hydroxide are needed, then I can suddenly solve the problem because I'm very close to the answer. I'm trying to find out what the volume of that solution is going to be required. So let's go from grams of acetic acid to moles, and then we'll use that guy to go forward. So let's go ahead and figure something out. In order to go from grams to moles here, we need to know the molar mass of acetic acid, which, just to remind you, is CH3COOH. That's what we're trying to find there. So how do we find that? Well, I have 2 carbons in here, so I'm going to say 2. And if you look at the periodic table, it's 12.01 grams per mole. And when you look over here, I've got 4 hydrogens, 1.01 grams per mole, if you read that off the periodic table. And I have 2 carbons, which are roughly 16 grams per mole there. So when you do all this math here, what you get is 60.06 grams per mole. So this is how many grams in a mole of acetic acid, CH3COOH. All right, so what I'm going to do next is actually start the final calculation. I know how many grams of acetic acid I have, 0.4112 0.4161 grams. Grams of what? Acetic acid. Let's use the chemistry here. The chemistry, the way to write it down in terms of a chemical formula. CH3, COOH. This is acetic acid. It's 0.4161 grams of that acetic acid. That's how much I have. Now I just figured out that acetic acid is 60.06 grams per mole. So what I'm going to find down here is 60.06 grams of acetic acid, CH3, COOH, per 1 mole of CH3, COOH. And I arrange it this way rather than flipping it over because I'm trying to cancel grams with grams. So if I stop the calculation now, all I've done, I know how much acetic acid I start with, I've just converted it to moles. But so now I'm at the molar part. I know how many moles of acetic acid. So if I go up to the reaction, which is balanced, by the way, we check that, what I found out is that for every 1 mole of acetic acid that reacts, it requires 1 mole of sodium hydroxide. So I use this fact here and I say, okay, from the reaction, for every 1 mole of CH3COOH, I require 1 mole of sodium hydroxide. That's how much I require. So moles cancels with moles. So now if I stop the calculation now, I've started with how much I have in my sample of acid, and I figure out how many moles of sodium hydroxide are required to react with it. That's what the reaction is telling you. That's what you've calculated here. How many moles? But when you look back at the problem, you're not asked how many moles of acetic acid. You're asked what volume of a certain concentration solution of this guy. So you're still being asked how much sodium hydroxide is required. You're just not being asked how many moles. You're asked how many milliliters or what volume of a certain stock concentration there. So when you see molar in a problem, you should read this as 0.550 moles per liter of sodium hydroxide. Moles per liter of sodium hydroxide. So when I go over here, if I continue this calculation on the second line here, and just kind of pretend that this is attached over to the end, it's 0.550 moles of sodium hydroxide for every liter of solution. So it's 0.550 moles of NaOH for every 1 liter of NaOH solution. Okay, and I arranged it like this so I could cancel moles of sodium hydroxide with moles of sodium hydroxide. Now, if I stop the calculation, the only unit I have left is how many liters of sodium hydroxide solution. And that's exactly what I was asked. I was asked what volume of sodium hydroxide solution is needed to titrate, blah, blah, blah. So if you do all of this, take 0.4161 times 1 divided by 60.06 times 1 divided by 1 times 1 divided by 0.550, what you're going to get is, let me just write it down here, 0.0126 liters of 0.550 molar NaOH. So I'm just saying you need 0.0126 liters of that solution. That solution happens to be what we already were given in the problem statement here. And if you wanted to convert this guy, this is liters. If you want to go to milliliters, you can shift the decimal 3 places. 1, 2, 3. So if I shift the decimal 3 places that way, I'll get 12.6 milliliters. So it's the same way. If you want to express it in terms of liters or milliliters, is the same way. So this problem is completed. What we figured out is we need 12.6 milliliters, which is the same as 0.0126 liters, of this stock solution given in the problem. And that's going to be how much. So if we set this experiment up, we'll have a flask of this amount of acetic acid, and then we're going to add this base to it. How much are we going to add? 12.6 milliliters. And at the moment that we add 12.6 milliliters to it, suddenly the solution is neutralized. It's neither acidic nor basic. Everything's reacted, and that's basically it. And so the general form of the problem, in a big picture sense, follows all the other titration problems. You're given an acid, and you're trying to find out how much base is needed to neutralize it. The only real hitch is that you need to use some of these other weird numbers that you may not have seen before in a chemistry problem to basically figure out how much acid you have. So first we start by writing the reaction, and then we look at what we have here. We have the density in grams per milliliter, and we know how many milliliters are in our vinegar sample. So we basically multiply them to find out how many grams of vinegar we have. Once we know that, We know this is kind of critical that only 4.12% by mass is actually acetic acid. So we take how much vinegar we have in grams, multiply it by that percentage. Of course, you have to convert it to a decimal, and that tells us how many grams of acetic acid are actually in the beaker on the table. Once you have that, we calculate the molar mass of acetic acid so we can go from grams to moles, which we've been doing a lot in chemistry. You should know by now that anytime you have grams of something, you can go to moles by using the molar mass conversion. So we know at the end of the day that we start with 0.4161 grams of acetic acid, we convert to moles, then we use the reaction to convert to moles of sodium hydroxide, and then we use the solution molarity to go from moles of sodium hydroxide to liters, and that's how we get our final answer. So it's the same general idea. You just have to resist that temptation when you're reading a chemistry problem to freak out and say, wow, this is totally different. How do I do this? You got to stop trying to put these chemistry problems in certain buckets. A lot of students say, well, this is this kind of problem, and this is this kind of problem, and this is this kind of problem. Try not to do that, because there's infinite ways I can construct a problem to make it a little bit different. What you need to do is understand fundamentally what you're trying to do. You need to use this chemical reaction to figure out, right here, the ratio between base to acid. That's how 1-to-1 ratio in this case, because it's balanced that way. So what you need to do is figure out through whatever math needed, find out how many moles of, in this case, acid you have. Then you can calculate the moles of base, and then from there you can go and find your final answer. So we just needed to use these numbers to actually inch our way to getting to that point. So trying to teach you how to think a little bit here. So when you see a problem that looks totally different, take a deep breath and realize that chances are it's not different. Chances are you just need to think a little bit about how to get where you think you need to go. So make sure you know how to do this. Follow me on to the next section. We'll do another titration problem to give you extra practice.
Learn anything at mathandscience.com.